Welcome to a new standard, a new semester, a new topic. I'm excited to see y'all. This semester we're starting off by talking about heat. And I know that you might think that's a pretty boring topic, but a lot of what we know about chemistry comes from what scientists learned from studying heat. Notice that we went from standard 3 to standard 5, so we will be doing standard 5 before standard 4 because that just makes a little bit more sense in my mind. So the learning targets and the success criteria that the district and I would like for you to be able to do. So today you're learning about something called endothermic and exothermic processes. Maybe you learned a little bit about that from physical science. And you'll know you're successful when you can define endothermic and exothermic processes and enthalpy, when you can differentiate between the two of them, and you could give examples. Heat involves the movement of molecules or particles when we're studying it from a chemical perspective. So I have a little thought experiment here. We're going to talk about how much motion something has. So imagine you have car A, and it's on the left, and it's going down a road, pretty fast down the road, but it's just going. So we have so much motion in this car. There's people in the car, and they're moving, and the car's moving, but it's just going in a straight line. Whereas car B, yellow car over here, it got in an accident. And so it's like actually off a windy, curvy road, and it fell off a cliff, and so it's rolling in the air, falling off a cliff. Everyone inside is going every which way, vibrating back and forth, and trying to get out, and the car's rotating around, and it's also falling in a straight line. So if we thought about what has more motion, even if car A on the left was going faster, car B would have overall more total motion if you added up all the different ways that everything inside is moving. Chemical molecules can move in the same way. So here I have a picture of a molecule. Here it's only two atoms bonded together, but the two atoms together could go in a straight line one way or another, and that would be called translation, or they could be spinning around, and that would be rotation, or they could just be vibrating back and forth, left, right, or together apart, and so that's called vibration. So there's all different ways that a molecule can move, and so kinetic energy is the energy of motion. You probably learned that in physical science. So there's just different types of movement that we need to think about when we're thinking about kinetic energy in chemistry. Here's an analogy of kinetic energy. So up here, I have two different pool tables, all right? Imagine playing pool, and so you hit your cue ball, and on the left, you didn't hit it very hard. The balls have broken, and they're all going different ways, but not going that fast. And so you can see that they have kind of smaller arrows showing from the ball which way it's going. Whereas on the right pool table, you hit the balls really hard, and so they're going really fast. And so they're, again, all going different ways, but they're going faster. And so, of course, if you've played pool, you know that if you hit the cue ball and it breaks, some of the balls go really fast that you hit, and other ones don't really go so fast, they go slower. So there's kind of like an average speed on the table if you were going to average all of them together. And that's what this graph up here shows. So the blue line is everything going slower. And so if you look at the x-axis here, kinetic energy is on the x-axis. So the further right you go, the faster they're going. So if they're all going pretty much slower, the blue curve just shows kind of they're all going in a close range. Whereas if they're all going really fast, then it spreads out. So some would be going really fast and some would be going really slow, but the average is higher. The average is higher. And so this is an analogy for temperature. In chemistry, temperature is related to the average speed of the molecules. So if the average speed is higher, then the temperature is hotter. So here's a question for you. We have 3 samples of water, 20 milliliters at 100 degrees Celsius, 40 milliliters at 80 degrees Celsius, and 60 milliliters at 60 degrees Celsius. So what has the highest average kinetic energy? All right, so remember, if you have an average, it doesn't matter how much of something you have. If you have 2 things or if you have 200,000 things, if it's an average, it's still just one number. And so the highest average kinetic energy would be in the hottest sample. They'd be on average moving faster. So it doesn't matter that there's only 20 milliliters. The one at 100 degrees Celsius would be like the red line here. It would be overall, the average would be higher. So in here, the average would be higher than, say, the one at 60 would be the coldest one, the blue curve, and so the average would be lower. So that's called an intensive property. Intensive means it doesn't matter how much of something you have, it's really the average that matters. You might have learned that almost no one in the world uses the Fahrenheit temperature scale. Almost the whole world uses the Celsius scale. So here's a list of countries that still use Fahrenheit. Only us, the Bahamas, Cayman Islands, Liberia, Palau, Federated States of Micronesia, and Marshall Islands. So really no other world superpower uses the Fahrenheit scale, but here we are. So we oftentimes have to convert between Fahrenheit and Celsius, and so you might have learned in a way previously in school where you like add 32 and you're multiplying by 5/9 or 9/5, but it's kind of confusing whether you add the 32 first or whatever. This is a way that will always work, and it's much easier to remember. You're going to add 40, regardless of whether you're going from Fahrenheit to Celsius, and then Fahrenheit's a bigger number always. Celsius is a smaller degree. So you're going to multiply by 5/9 to make something smaller. 5/9 is less than 1. So if you're going from Fahrenheit to Celsius, multiply by the number less than 1, multiply by 5/9. Whereas if you're going from Celsius to Fahrenheit, you're trying to make it bigger. You'd multiply by 9/5, and then you'd subtract 40. This always works and is much easier to remember. There is a third scale that you may or may not have learned about in physical science. It is called the Kelvin scale. The reason we use the Kelvin scale is because you might have noticed from algebra and other mathematical calculations that when you start introducing positive and negative numbers into problems, it becomes much harder and you're much more likely to get mistakes. So, you could have negative degrees Celsius when something gets really cold. Well, Lord Kelvin was like, that just makes all my calculations harder. Why don't we just make the coldest something we could be 0, and then we just go up from there. So the Kelvin scale has the same intervals as Celsius. It's just that it takes the coldest temperature possible, which is 273.15 degrees, and it makes that 0 instead of negative 273.15. So to get from Kelvin to Celsius to Kelvin, you're going to add 273.15 to go from Celsius to Kelvin, or from Kelvin to Celsius, you'll subtract 273.15. Here's an example problem. Let's convert 160 degrees Fahrenheit to both Celsius and Kelvin. We will go from Fahrenheit to Celsius first. So again, we add 40, and so 160 plus 40 is 200. We're going to make it smaller. Remember, Fahrenheit is a bigger scale. If you think about your body temperature, 98.6 would be Fahrenheit, but 37 in Celsius. So we're going to make it smaller. So 200 times 5/9, that's less than 1, to make 111, and then we'll subtract 40 to get 71. And you can't go directly from Fahrenheit to Kelvin. You have to go to Celsius first. So we just found that 71 was the degrees in Celsius, so then we will add 273 and we'll get to 344 Kelvin. One thing to note is that we have degrees Fahrenheit, degrees Celsius, that little circle, but we don't say degrees Kelvin, it's just Kelvin, so there's no circle. Lay people's definition of heat, the non-scientific definition of heat, is very different than the chemistry definition of heat. The chemistry definition of heat, it only talks about when energy is being transferred. Heat energy is being transferred from one thing to another. So if something's just sitting there and it's not heating up the surroundings, or there's no temperature change, then actually there is no heat. There's only heat flow. Okay, so matter doesn't have heat, but it does have internal energy. All those things that are moving around, we talked about the average motion being related to the temperature. So it definitely has energy, but heat only exists when energy is being transferred from a hotter object to a colder object until they are the same temperature, and that is heat flow. A key thing to be able to figure out or learn from this unit is the difference between heat and temperature. So here's a chart that compares them. Heat on the left is represented by the variable Q, okay, whereas temperature is T. Heat is the total energy being transferred. So heat only exists, as we talked about, when energy is being transferred. So heat is the total amount being transferred, and so it's what's called an extensive property. It depends on how much material there is, because think about it, if you had like a couple drops of hot water versus a whole gallon of boiling water, the gallon of boiling water would be able to transfer more heat out than a couple drops of hot water. Whereas we talked about before that the temperature is the average kinetic energy of all the molecules, so that's an intensive property. It doesn't matter how much it is, it would still be the same average. So again, heat only, we're talking about heat flow, so it flows from hotter to colder, whereas temperature raises when something's heated and falls when something's cool. The unit for heat is joules or calories, whereas in temperature it's Kelvin, Celsius, or Fahrenheit. And we measure heat with something called a calorimeter, which we'll talk about a lot next time, versus a thermometer, which you are used to for measuring temperature. How is heat transferred? Well, it's transferred differently in solids versus in liquids and gases. Remember that I said everything is always moving. All molecules are moving in this universe, except if we ever got to absolute zero, which we haven't, but all motion would stop at absolute zero. But except at absolute zero, everything is moving. So solid things are moving. The molecules inside your computer are moving. The molecules inside your pencil are moving. They're vibrating back and forth. And so Imagine I had a cold pan and I put it on a hot burner. What would happen? Well, the molecules on the hot burner would be vibrating really fast, and in the pan much slower. But when they come in contact, imagine the contact was right here, so it starts shaking up one side, right? So this is like the contact with the burner, and then they'll start shaking, 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 and now the molecules of the pan are vibrating much, much more, and so the pan gets to be the same temperature as the burner. So it's vibrations and in contact when it's solid to solid. On the other hand, for liquids and gases, it's all about molecules colliding into each other. So we're going to talk nonstop for the rest of the year all about collisions. So chemistry is a pretty violent process, actually. It always takes place with things crashing into each other. And so liquids and gases, the molecules can move different places, and so they crash into each other like the balls on a pool table. And so hot molecules are going faster with more energy, and so they can collide into something slower with less energy, and when they collide, then they'll have more like an average of the two energies. So that is how heat is transferred with liquids and gases. If we wanted to do an example, we could draw a particle model showing heat flow of hot coffee versus room temperature coffee. So in hot coffee, here on the left, the particles will be going really fast. So the way you can draw fast is you draw the little circles with a big arrow, and they're going all different ways. Notice they're not all going the same speed or direction, but there's like an average, you could say. And so the hot coffee at 85 degrees, the molecules will be going really fast compared to the molecules in the room. And so as they're hitting the sides of the cup the cup would start warming up, and then that would vibrate faster, and then the faster vibrations would interact with the air molecules in the room, and that would speed those up too. So you could say that heat is being radiated from the cup with these little red arrows. Whereas on a cold cup of coffee, or a cup of coffee at room temperature, the molecules are moving slower with smaller arrows, and there wouldn't be any heat transferred because the room temperature molecules would be going about the same average speed. The concept of system versus surroundings and endothermic versus exothermic is like a key point of this whole unit. This is something you absolutely have to master. So the system is the part of the universe that we are focusing on. And so it could be your chemical reaction, it could be a balloon, it could be a cup of coffee, it could be the air in your tire of your car. But basically it's what you're studying, what you're focusing on. And then the surroundings is literally everything else in the universe. Okay, and so we're going to constantly talk about how heat energy is transferred from one thing to the other. So there's two words. One's called exothermic, like an exoskeleton in biology was the skeleton on the outside, right? Versus endothermic. Endo means inside. And so exothermic is when energy goes out of the system, and endothermic is when energy goes into the system. So this totally depends on your frame of reference, because you might be studying different things at different times. Here's an example. You have a Bunsen burner underneath a beaker of water and it's heating it up. Is this an endothermic or exothermic process? Well, so here's your Bunsen burner, here's your beaker of water. So it really depends on what you're looking at. Are you thinking about the flame, the chemical reaction going on as the methane's burning in the Bunsen burner, and then that's what you're studying? Or are you talking about the water that you're heating up? And so here, imagine that we have the system is water. And so if the system's water, it's taking in energy. Heat energy is being transferred from the flame to the water. So heat is going into the water, and that would be endothermic, okay? On the other hand, if we were studying the flame, then we would be talking about the flame giving off heat and going everywhere, including heating up the water. And so if you think about the system being the flame, then the surroundings is everything else, including the beaker of water. And so we would say that this is an exothermic process because heat is moving from the flame to the surroundings. In your notes, we have this chart that's the difference between the endothermic and exothermic process. We're going to go through it a little bit at a time. I've covered up different parts of it so that way you can focus on the part I'm talking about. So endothermic process is when heat is transferred from the surroundings into the system, whereas exo is heat transferred out from the system to the surroundings. Again, endo means in, exo means out. Here is a picture version of that. So here on the endothermic process, remember that would be heat coming from the surroundings into the system. We see surroundings, and then energy is being transferred, arrow, into the system. Whereas on the other side, exothermic, we have our system, energy is being transferred out into the surroundings. So we're going to use arrows a lot of times in this unit to like show which way the heat is flowing. Another way to represent an endothermic and exothermic process is with a chemical reaction. And you can actually write heat as a reactant or a product in the chemical equation, even though it's not a true chemical. So here's an example. So dissolving ammonium chloride here, so ammonium chloride solid, you put it in water and it becomes aqueous. So heat is involved in that process. So if you add heat, more will dissolve. And so heat is a reactant. So heat is taken into the system, versus dissolving calcium chloride. Calcium chloride, when you put it in water, will release heat. Okay, so heat is leaving as a product, and so that is an exothermic process. Remember, endo taking it in, exo putting it out. Another example, and I apologize, there is a typo here. So here on the left, it says melting ice. So if you have heat plus solid ice or solid water, then it'll turn into liquid water. That's obvious, right? So the ice is taking in heat. And here is the typo. I apologize about that. This should be freezing water. It will be fixed in your notes, just not here in the presentation. So you were freezing water. So this would be H2O liquid. And so if we take H2O liquid and we freeze it to solid ice, this would be a solid, then heat would be released as well. And this is just a general way to do what we did up here. These were specific examples, but generally we could say heat plus A goes to B, or it could be heat plus AB goes to CD. But basically heat is on the reactant side for the endothermic process, and heat is on the product side for the exothermic process. Another way to represent this is with a potential energy graph, or just energy graph. So here we have two lines. We have, this is the reactants before the heat is transferred, and then the products. So the up arrow or the down arrow says whether the system, okay, is taking on heat energy, whether it's being transferred to the system. So if you had less energy in the reactants and you added some energy, then the energy of the products would be higher. Versus if the reactants had higher energy and then they gave off some of their kinetic energy, so the reactants cooled down, the products would have less potential energy. And I told you that Q was the abbreviation for heat, whereas T was for temperature. So Q, if you're absorbing heat energy, then it's a positive change, right? So Q would be greater than 0. Whereas if you're releasing heat energy, if the system is releasing heat energy, then the Q would be negative, Q less than 0. And this is the most important part, because in chemistry we're talking about chemical reactions, which is breaking and forming bonds. So a bond is stable, right? Things want to come together and form bonds. So it actually takes energy to pull them back apart, like stretching apart a rubber band. So when you break bonds, you actually have to add energy. So it's an endothermic process. If the system is the chemical and you're going to break its bonds, energy has to go in to pull it apart. Okay, so this could also just be the van der Waals forces or the London dispersion forces, but basically if you're breaking bonds or attractive forces, then the attractions are broken, which has a higher chemical potential energy. Energy had to go in, and then overall they have a higher energy. So you started off with lower energy and then went to a higher energy. So this is increasing the kinetic energy. Whereas if you form bonds, okay, so if chemicals come together, bond, and they're more stable, then they have a lower energy, okay? So they were higher energy when they were pulled apart, they release heat energy, and now they're more stable. We are going to use this, we call it a LOL chart, which is different bar graphs to represent the heat that is flowed throughout this unit. And so we have on the left the initial, and there's different ways that kinetic energy is stored, or potential energy. And so we're going to talk about different columns throughout this unit. Right now we're just going to talk about the temperature column, which is the first column. And then we're here in the energy flow. The system goes inside the circle, the surroundings outside the circle, and then we'll show whether energy goes in or out. And then we'll have a final bar graph. And the key is that the actual amount of boxes you shade doesn't really matter as long as you're just consistent. We're just trying to get a picture representation in our minds. So an example will follow. So imagine we have a cup of hot chocolate that's sitting on the counter, describing how the arrangement and motion of the particles from the initial to the final state and how the energy flows is much easier with this LOL diagram. So we're going to start off initially. We have a hot cup of hot chocolate, okay? And it doesn't matter how many boxes we choose. We shouldn't choose one, but as long as we choose 2, 3, or 4 boxes, then we know that it's hot. So the bar graph we color in here in red is three boxes in this example. Then our cup of hot chocolate is going to cool down, right? So it actually transfers some of its heat out to the atmosphere. It's going to heat up the cup, heat up the atmosphere, and then it loses some of its energy. So you can see final, after it transferred out 2 blocks of energy, now it has 1 block of energy. And so we could put that into words up here. Coffee particles, which are moving fast, right, because they're hot, they collide with the surrounding particles. Could be the cup, could be the air, but those are going slower. And so in the collision, imagine like on a pool ball, on the pool table, the cue ball, it will collide it into the surroundings, and so it will make the surrounding molecules faster, and it'll slow down themselves, making them slower. So the hot chocolate will cool down as its molecules go slower. So that's it for the first day of Standard 5A. Go through the checklist and make sure that you can do these things, whether you can define endothermic, exothermic, and enthalpy. Enthalpy we're going to talk about a little bit more next time, but endothermic and exothermic certainly. And if you can differentiate and give examples of those. All right, see you at the next lecture.